F is a period 2 with ft equal t for t between 0 and 2. Sketch the graph of f, find the Fourier series of f, and deduce Leibniz series. Now we need to sketch the graph. T (0 to 2). So the graph look like this on 0 to ft equal to t, and you copy that for the other interval. So this is a graph of the function f. Now we need to compute the Fourier series. Let me call ft the Fourier series of the function small f. The Fourier series of small f is a0 over 2 summation n from 1 to infinity, an cosine n pi t over l, bn sine n pi t over l. Here's l is half of the period, and the period 2, so you have 2l is 2, or l is 1, half the period is 1. In our case, l equal to 1. So this is a0 over 2 an cosine n pi t bn sine n pi t, n from 1 to infinity. We need to compute the coefficient. a0 1 over l minus l f ft dt, and in fact you can choose any interval of length 2l you want. 1 over l, I choose 0 to 2l ft dt. And in this case, because we work with the interval 0 to 2, so maybe more convenient for us to do 0 to 2. a0 in our case 1 over l, 1 over 1, 0 to 2, ft equal t dt. So 1/2 t squared from 0 to 2, 1/2 times 2 squared minus 0 squared. So a0 equal to 2. We computed. There's the first coefficient here. And an, now we do an. An equal to 1 over l minus l to l ft cosine n pi t over l dt, or you can use other interval. 1 over l 0 to 2l ft cosine n pi t over l dt. So in this case I use 1 over 1, 0 to 2, ft equal t cosine n pi t divided by 1 et. You do computation, you see this is 0. That is for an. An equals 0. Now we compute bn. bn 1 over L 0 to L ft psi n pi t over L dt 1 over 1 0 to 2 t psi n pi t divided by 1 dt. You do computation integration by parts. You should have minus 2 over n pi integration by parts. So we have, this is our Pn. So we have everything here. You can plug in this formula. The Fourier series is A0, A2, so 2 over 2 is 1. An 0, so we only have Bn. And 1 to infinity Bn equal to this term minus 2 pi. So I can just bring this out of the sum because just a number. Minus 2 over n pi psi n pi t. Then you move it now. 1 minus 2 over pi summation psi n pi t divided by n, and from 1 to infinity. Now this is a Fourier series of f, and conversion ft, the Fourier series of f, equal to is converse to small ft. So this is t0 if f is continuous at t0 and is converse to average of the limit ft t tend to t0 minus plus limit ft t tend to t0 plus if f is discontinuous at t0. So this is a theorem of conversions of Fourier series. Now we have this Fourier series, and we need to show the Leibniz. We need to deduce Leibniz series. Here's our Fourier series of f, and here's the Leibniz series. You see that in the Leibniz series, we don't have any terms 1 over even numbers, right? We have 1 over 1, 1 over 3, 1 over 5. So the terms with n even are all 0. So we want psi of n pi t's are 0 and even. And we want alternating psi. So we have positive, negative, positive, negative. So I want to choose this term, psi n pi t 0 there, and alternating psi. Choose t so that it is 0 when n even and alternating psi. So plus minus when n odd. So one option I can do is to choose t equal to 1 over 2. T is equal to 1 over 2. The Fourier series become f 1 over 2, 1 minus 2 over pi psi n pi 1 over 2 over n from 1 to infinity. So you see that n pi over 2, this unit circle, pi over 2 here, n is even, so we have 2 pi over 2, 4 pi over 2, 6 pi over 2, 8 pi over 2. So these are 0. That's exactly what we want. And we want, well, n is odd, so we have 1 pi over 2, which gives us plus 1. 3 pi over 2, which gives us minus 1 for psi. 5 pi over 2, 7 pi over 2. So which satisfy what we want. Now let me write down the first few terms. 1 minus 2 over pi psi pi over 2 divided by 1 psi 2 pi over 2 divided by 2. Then you have psi 3 pi over 2 divided by 3 psi 4 pi over 2 divided by 4 psi 5 pi over 2 divided by 5, and so on. So you see that for all the terms n is even. Psi 2 pi over 2, so this one 0, 2 pi over 2, 4 pi over 2, all these are 0. This disappear. Now psi pi over 2 plus 1, you have plus 1 here. And then you have minus 1 over 3 plus 1 over 5. So alternating sign. 1 minus 2 over pi, 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. So that's what is. So this is a Leibniz series. These terms, Leibniz series here, which is actually this series. This terms is a Leibniz series. I call it L. The Leibniz series. So we have Fourier series at 1 over 2, 1 minus 2 over pi times L. So bring 2 over pi times L to the left and bring Fourier series to the right. 2 over pi L equal to 1 minus f 1/2 L equal to pi over 2 1 minus f 1/2. So all we need to do now is to compute f at 1/2. F at 1/2, 1/2 is a point of continuities. 1/2 is here. 1/2. So f of 1/2 is f of 1/2 equal to 1/2. So the Fourier series converts to f of 1/2. So we say that small f is continuous at 1/2. So the Fourier series at 1/2 converts to exactly f of 1/2, which is 1/2. So Leibniz series L equal to pi over 2 times 1 minus 1/2 pi over 2 times 1/2, which is pi over 4. And that's what we need to show. L equal to pi over 4. So our question is L equal to pi over 4. So this is L we talk about. L equal to pi over 4. We are done.